So before we proceed with the discussion that we are having, so maybe I'll focus a couple of minutes on after reviewing the assignments yesterday, we saw that there are some couple of recurring mistakes that people have done. Right. So one mistake that obviously all of you have done is this. The assignment was something like this, right? We had a GM, which was an ideal GM, small signal, VI, some R, and there were these switches and some LPF connected here. The most common thing I saw people do was this. And there was a PMOS equivalent of that also, because it's a transmission gate. So the issue with this is, I mean, whoever had made this mistake, I had pointed it out. What is the quiescent point at this node? Quiescent voltage? It's 0, right? So because how do you find quiescent? There is no input, right? So this is 0. This is obviously hard ground 0. There is no other biasing anywhere, right? So this will naturally be 0. Now, what's the problem if that is 0? You might think that, okay, the NMOS is probably max on to the maximum level, right? When the gate of the NMOS goes to VDD, the VGS is VDD, that is the maximum that you can get. But what happens if the signal swings in the negative direction? Right? So ideally, you would want to see the signal going like this, right? I mean, there will be positive and there will be negative of the signal, and it will be around the quiescent point, right? If this is 0, so this is obviously negative. Now, what's the issue if it's negative? Now, if you see that, I assume all of you have taken at least one device course. So what is the cross-section of a MOSFET? If it's an NMOS, the gate, you can assume this to be drain or source, doesn't matter, because ultimately when the switch is on, this is supposed to be in linear region, that is, you do not expect too much voltage drop across drain and source. So ideal case, assume drain and source are shorted, which essentially means that this is a PN junction here. So this is a PN junction, this is a PN junction, right? So you would expect for a proper operation of a MOSFET, these PN junctions to be forward biased or reverse biased? Reverse biased, right? So you would want all the current to flow in this direction in the channel in the presence of inversion charge. So this is essentially a magnetic area device. You have N in the drain side, electrons in the source side, and electrons in the channel. It's a magnetic area device, unlike a BJT. So which essentially means that there is no PN junction between the drain and the source and the channel when inversion has taken place, right? So, I mean, what happens if this PN junction now gets forward biased? So this is a PN junction here. This is a PN junction here. So what happens if this PN junction gets forward biased? The current that is supposed to flow from the drain to the source to the channel will go into the diode and will not come out, right? So, which essentially means that, and when can it go forward biased? Because this is grounded, the body is grounded, right? When this guy goes negative, then you have a problem, right? Sorry, it's opposite direction. So when the drain or the source goes negative, then you have real problems. So this guy will have problems, right? You might, in your simulation, you might not see hard clipping because these are not like those ideal PN junctions that we study in basic electronics, that beyond 0.7 or beyond 0.3 or whatever, it starts saturating. So you are going to see a considerable amount of current flowing into the body. And there will be obviously be distortions because of that. Right? And more importantly, which doesn't get captured in your simulation as much, there can be issues of latch up. I have not talked about latch up, but whenever you have current flowing into the body, it can generate. Your body is also not like a hard ground, right? It also has resistances because this is lowly doped P. Right? It's not a very highly doped P. It's not a metal. You are going to have resistances, which means that when current flows, you are going to have positive and negative, significant amount of positive and negative voltages across these PN junctions, which means that not only across these PN junctions, across the substrate, which means that there can be a lot of, this substrate, which is assumed to be hard ground, can have negative charges or negative voltages different places of the substrate. Now, if some other device is also connected on the same substrate, then that can cause similar problems. So one such problem is called latch up. You can read up about latch up on your own, but the issue is that you do not want forward bias PN junction with the substrate, right? So, and if you do not take care of the bias, then this can be a big problem. Okay. So what is the easy fix? So in the assignment, what can be the easy fix? So how do you ensure the quiescent voltage at this node is not zero? You can give many things. You can, this is a small thing. If you assume this to be a small signal ground, right? So you can obviously give a battery here, right? So lift that voltage. And if you do not want to take that risk and say that, okay, I didn't know this, this can be weak, then you can have a separate resistance, some V bias resistance here, right? So that can give you the requisite amount of voltage at this node. But obviously, if you have this RB has to be, if you want this voltage to be of certain value, which is equal to VB, what should be the relationship between RB and R? Let's say I apply VB wherever I have, I want approximately VB here. So what should be the relationship between RB and R? RB should be equal to R, much greater than R, less than R? Much less than R, right? But if you have much less than R, then do you foresee a problem? Bias will be set, but signal-wise, the effective resistance reduces. So the fix can be, can you suggest a fix? Pardon? You want a battery in parallel to R. So how will that help? It will set, but what about the signal wise? And that is a desirable. I know, but for the small signal model, for the incremental picture, is it a desirable thing? Sure, it is going to hold that value. But where will the current from the GM go? It will go to short. And is that a desirable thing? No, right? So it cannot be done. So what else can be done? Pardon? Okay, implementation is a different thing, but I mean, even if you put a PMOS, you are going to see an effective resistance, right? Something here. We can put an inductor also. Right? We can put an inductor. Definitely, we can put an inductor. Just that you have to ensure that the value of the inductor is such that what will be the constraint? The impedance of the inductor at what frequency should be much greater than or less than or whatever. At DC, no problem, right? Inductor gives zero impedance. So DC is set, but at the frequency of interest, so it should be omega, some omega times L should be much greater than whatever the effective other resistance at that node, right? So R effective. But which omega will you choose? There are two omegas here, right? So one is the input omega, which is omega n, and you have down converted here, which is approximately around DC, right? Which is 1 megahertz or 2 megahertz or whatever. So input omega was at gigahertz. So which omega would you choose? Omega L to be much greater than RF, omega in or omega close to DC? Omega in. Why omega in? Why not omega close to DC? At this point, the frequency is omega in. Again, okay, I understand what you are saying, but can you qualify it a bit more? What do you mean at this point the frequency is omega in? Right. So it is before down conversion, right? So what is happening? The current that is coming here is getting mixed and getting down converted here, right? So essentially, you can think the mixer on the left-hand side of the mixer, you have all the RF components. On the right-hand side of the mixer, you have all the DC components, low frequency components, right? So the dominant signal on the left-hand side of the mixer is high frequency, right? It is at RF, right? So this is the RF side. And this is the baseband side. So when you are dealing with RF side, then you obviously deal with the frequencies corresponding to the RF signal. And so hence omega L to be much greater than R effective would suffice. What else, if you do not want to use an inductor, then what else could you have done? Yes. Yeah, sure. But okay, do you see an issue with that? In this particular example, you can put, right? So his point is if I put a DC voltage here, so VDC, so this current will be GM times VDC, and it is going to go into some effective resistance, and I can tweak the value of VDC to set the value. Sure, in this particular example, sure, because I gave you GM to be ideal and all, right? So essentially what you are trying to say is that the GM sets the DC operating point at the output, which is actually not a bad thing to do, because in the next assignment that you are going to do, the LNA that you are going to design, you are going to club with the mixer, right? So obviously the output of the LNA has a DC operating point. So that's not zero, right? So that can be used to bias the mixer, right? But it's not necessary that can be the optimum operating point for the mixer, right? If you are not taking care of the, let's say mixer of, in this example, what is the optimum operating point of the mixer? Let's say you do not have any other information. You want to ensure that swing here is such that it doesn't clip on either side. So what should be approximately VDD by 2, right? So, but it's not necessary that the LNA that you are designing should have the output to be at VDD by 2, right? In fact, probably you would want the output to be quite high, right? Output quiescent point. Because if it's low, then the cascode transistor of the LNA that you are designing might go out of saturation. On the upper side, you do not have a problem if you have an inductor on top, right? Does that make sense, the statement that I made? So the LNA that you are designing for the assignment, I assume you are using, if you are using the one that has been covered in the class, Then you have a common source, then you have a cascode. On top of that, you probably have an LC tank. The LC tank can go above VDD. The voltage on the top of the cascode can go above VDD. That's not a problem, right? But if you directly use that operating point to bias the mixer, then this mixer is going to have a problem because this guy will be at a much higher voltage, maybe around VDD, quiescent wise. When the signal goes above VDD, what can happen? So I am now drawing the switches only. So let's say this is biased approximately at VDD, maybe 0.9 VDD, maybe 0.8 VDD. I mean, don't assume it's VDD. But when the signal swings, this signal can go much higher than VDD. So what do you see an issue with this? I can't hear you. The switch has a problem, right? Because the switch, this voltage that can go maximum is how much? It can go VDD, right? Maximum you are driving with a square wave, this can go to VDD. So naturally, when this goes above, if this is, let's say, VDD, so clearly, even if I assume threshold voltage to be negligible, which is definitely not the case, this guy is getting clipped off. If I take threshold voltage into account, then maybe till here it is getting clipped off, right? So the moot point that I'm trying to make here is that you should be cognizant about what operating point you are going to you are setting. If the previous block is not able to set the operating point as you desire, then you have to take corrective measures and then set the operating point. Now, in many places, it is not possible. In this case, it is definitely possible. So can you now give me an alternate way of biasing this? Yes. Oh, I'll come to that, right? Why? So his point is that there is I mean, if I bias it with a PMOS transistor, then this is good, right? So there is another reason why people don't use PMOS transistor. I'll come to that today. Right? But let's assume that, okay, since we are talking about it, I can let me spend a minute on this. So generally, NMOS and PMOS are essentially complementary to each other in all electrical respects, right? I mean, this design is different, that's fine. But electrically, if I show you the IV characteristics of a PMOS and an NMOS, and I don't tell you whether I'm plotting with VDS or VSD, whether I'm plotting with VGS or VSG, whether I'm plotting IDS or ISD, you will not be able to tell whether it's a PMOS or a NMOS. They're absolutely identical, right? But there is one key difference. In general, the PMOS beta or mu p is lower than the mu n of the NMOS, which used to be the case even till a few years back. But right now, there are symmetric devices which are being made because of advances in devices. But let's still assume that even the one that you are using, the technology that you are using, it also has mu n more than mu p. So let's stick to that, right? If mu n is more than mu p, so then obviously for the same size of the device, which device is going to give away a lesser Ron? NMOS or a PMOS? NMOS, right? So if I have to design something for the same Ron, then effectively it means that the W by L of the PMOS will be higher than the W by L of the NMOS, right? The PMOS has a lower strength. If I have to make it as same Ron, then I have to make it bigger and fatter, right? So what implication does it have in terms of capacitances? High capacitance, right? So for the same Ron, you are going to get more capacitance in a PMOS than in a NMOS, right? So normally when you do common source amplifier design, or when you are biasing anything for saturation operation, this translates to saying that for the same COX, you are getting lower GM in PMOS than in NMOS. Right? Does that make sense? For the same oxide capacitance, oxide times W by L, right? Times WL, the total capacitance, same CGS, let's say, for the same CGS, you are getting lower GM in a PMOS than in an NMOS. which essentially translates to saying that PMOS has a lower FT than an NMOS. Right? So PMOS is a slower device than an NMOS. So what implication does this have here? One is, if you want to pass a signal, these guys are, there are two implications here. One is these guys will be driven by some set of inverters, right? In your assignment, you assume these are ideal waveforms, but when in a real receiver, you have one sinusoidal waveform somewhere, you have to convert it into square wave and then drive it using set of buffers. Now, must have done 619 or you are doing 619. What is the implication on these inverters if the capacitance here is higher than the capacitance there? Let's say this is Cp, this is Cn, and I say Cp is greater than Cn. What implication does it have on the sizing of the inverters?
The aim for both of them has to be the same, but the bottom inverter should be larger.
Right. So essentially, these inverters should be sized more than these inverters. Right. Otherwise, you are not going to have same rise and fall times. You will not be able to get the same, drive the same capacitive load, which essentially means that you are going to consume more power. Right. So this logic is not true if the PMOS was having the same strength as the NMOS. Why? Because then by adding two, it's almost equivalent to saying that I am adding two devices in parallel. If I add two identical devices in parallel, then effectively the amount of power consumption scales with R-on. Right? If the R-on goes down by a factor of 2, power consumption goes by a factor of 2 up, there is a justification. But in this case, the power consumption will go up by more than a factor of 2 than if I reduce the R-on by a factor of 2. Right? Because to reduce the R-on by a factor of 2, you have to increase the W/L of the PMOS by more than a factor of 2. Right? Make sense? So power consumption wise, this is not an ideal scenario. So, okay. So let's say I am okay with the power consumption. There is another problem. Another problem is you will never be able to ensure that when this guy turns on at the simultaneous same time instant, the PMOS also turns on. Because they have different threshold voltages. Right? You can probably ensure the rise and the fall times. I mean, this rise time and this fall align. But you are never going to ensure that the threshold voltage is exactly at the midpoint or whatever you want it to be. Right? So because of device mismatch, because of variations in process, they will always be off. Which essentially means that these two devices are never going to turn on at the same time. Right? So if two devices are not turning on at the same time, in a mixer, this particular topology, what can be a potential problem? Let's take an example. Let's assume that S1, S2. Let's assume that because of this turn on difference, let's assume that there can be, let's say this is S1. This is effective S1. Effective, I mean that when the device actually turns on, not the waveform. When the device turns on. And if the device does not turn on exactly the same time, it is quite possible that S2 can be like this. Right? So there can be this period where both of them are on. Right? So when both of them are on, what can be the problem? Oh, why static power? I mean, these are, when you say static power, can you define? So consider this architecture, and these are the S1 and S2 that I have drawn. So what can be the problem if both of them turn on simultaneously? Consider the charge stored on the capacitor. What's going to happen? Pardon? There will be offset. Assume S1, S2 ideal and everything. Both of them are turned on. What is going to happen to this voltage? This is V1, this is V2. There will be charge sharing between these two capacitors, right? So you are losing the charge on the capacitor, right? So that can be a problem, right? Because ultimately the voltage across the capacitor is essentially the information of the baseband. You are losing part of the baseband information, right? So that can be a problem. What else can be a problem? Let's say it's the other way around, right? It doesn't share, but it goes like this. Non-overlapping, and not by a small amount, but let's say significant amount. Then what can be a problem? This is less of a problem, but no, what can potentially be a problem?
Signal is not going to the mixer.
Exactly, right? So this essentially means that there is this time when both the switches are off, right? Which means the signal is basically not passing to the capacitor at all. You would want either the signal to go into the top capacitor or the bottom capacitor, right? If a signal is not going, which means effectively you are losing information during that time instant, right? So there will be a loss, right? So, pardon? Yeah, it's similar to dead time, right? So you are, but still this is not that much of a problem than having overlap, right? So it's better to do this non-overlap than the overlap, right? But so there is another problem by using PMOS. The another problem is, yes, yes. The assumption is because of the rise time and the fall times are different, then effectively S1 and S2 can have this difference in turn on times. That's I am extrapolating that argument. Okay. Yes. So this current, okay, I have not shown you that what is the conversion gain of a mixer. I'll do that. But intuitively, you can assume that this current was supposed to either go and get dumped onto capacitance, this one or this one. Correct? So if it doesn't, right? So the capacitor doesn't have any information of the input during that time. Right? So very, very top level sense, you can assume that there's a loss of information. We can show that this causes a loss of gain. I think of it this way. I mean, if the switches are always off, there is no information. Right? Yeah, exactly. But okay, losing in terms of what we should have gotten, right? Not with respect to the flow charge stored in the capacitor. We are supposed to get from the input, but we are not getting. Yes. Yeah, but the fault of it is the problem of those external circuits which are driving these switches, which is true. But the fault of the PMOS is the PMOS is forcing those sizes to be higher, right? And also PMOS and NMOS do not track each other. Their threshold voltages do not track each other. If everything was a NMOS or everything were a PMOS, then let's say a threshold one NMOS has a threshold voltage of 400 millivolt. With a fair amount of accuracy, you can predict that the next identically laid out sized NMOS will also have a threshold voltage of 400. But that's not true for an PMOS. If you have a NMOS which has a threshold voltage of 400 and a PMOS maybe at some corner has a threshold voltage of 400 also, minus 400. But you just slightly change something, this PMOS can become minus 450, while NMOS remains at 400. So the turn-on times can vary a lot because they are completely different set of processes the way you make a PMOS or an NMOS, right? Okay, fine. So the key takeaway is that it is better to use, I mean, having said all of these, you can still use a PMOS, a transmission gate, right? If you are aware of these things and you are taking care of these things, right? But simply vanilla using, it's a problem. And I am not penalizing any of you for using a transmission gate, because at this stage, I don't expect you to understand that that level of intricacies. And it doesn't always show up in your design also, because you are using ideal clocks, right? So that's okay, but it's better to know about these things. Okay. So now the problem that you are going to face in the next assignment is how are you going to bias the mixer? Because your LNA is going to have some operating point. Mixer needs some operating point. You can obviously put this inductor and bias, but inductor again, takes a lot of area. Maybe it's okay for the frequencies that you are using, but in general, if you do not want to use an inductor, there is another way of biasing this, is this, right? So we understand that this is at fairly high frequencies, right? This is at omega RF. So if I put an AC coupling capacitor size such that the value of the impedance of the capacitor is much lesser than the effective Thevenin resistance it sees around it, right? So then this is a short at a single frequency. Then I can probably use an RB, which is much larger than this RGM. In this case, RB can be much larger than RGM without causing any loss of, signal, or without causing any additional drop of the operating point, right? So you can have this. Okay. But if you, this is the one where I have used a capacitor at this end, but the one that we were discussing in the previous lecture was having a op amp here. And this can be a fully differential op amp or two single-ended op amps. I'll leave it up to you. So in this case, how would you, in this case, the op amp also needs some biasing, right? So you want some bias voltage here, you want some bias voltage here for the op amp to operate, right? So what is the typical bias voltage you require for an op amp at the input side from whatever you have designed till now? Can't hear. VDD by 2, approximately, right? So this is approximately VDD by 2. As it happens, this is also approximately VDD by 2, so you do not have a problem then. It would have been a problem if the requirement were different on both sides. Okay. Okay, fine. So now before I move on, any questions on this? Yes, a forward bias issue can come in. Whenever you have a PN junction, you can have a forward bias issue if you're not careful, but the condition need not necessarily be the same for which the forward bias happens. Source and body are? What about the drain side? Can happen, right? So there is another issue why it's shorting the source and body or the source and drain. So let me address that also, because this is a switch, right? Ideally, this is a switch. Have it a NMOS, have it a PMOS, doesn't matter. So can you really define which is source and body in a switch? And how do you define, if at all, which is source and which is drain? What decides which is source, which is drain? Higher potential, right? Higher potential is the drain. Or otherwise, I can say that from wherever you are drawing the current is the drain, others is the source. Now, depending upon the input, the current can go either this side or that side. Right? It's a sinusoidal input. So the effective current, if it is zero bias, the total current can go either on the left or the right. Assuming there is a DC current into the switch. But if there is no DC current, which typically is the case in a switch, so then the total current can either go left or the right instantaneously. Does that make sense? Which means the drain and the source keep on switching. So then from where will you connect the body? You cannot, right? So what is the solution then? Pardon? I can't hear you. Shorting, right? So essentially you connect it to ground, right? So that's the safest option. Right? If you have a PMOS, you connect it to VDD. So basically you would want it to be connected to the highest potential, or lowest potential in case of a NMOS, or the highest potential in case of a PMOS. Right? Make sense? So this also gives you an idea why PMOS is a problem, because these voltages will never go negative if you are using the LNA that we have talked about in the class. Right? If you recall, these voltages can never go negative, right? Because the NMOSs can go, if the voltage goes negative, then the transistors will go out of saturation, right? In principle, it cannot go, but even if it goes, it will not work. But it can go above VDD, right? So if you use a PMOS, this is not a very solid argument, but you can have other architectures to counter this. But if you use a PMOS and connect it to VDD, and this goes above VDD, then this PN junction here is going to get forward biased. I should not have drawn it like this. Should have drawn like this. Right. So that can be a potential problem. That is one of the other reasons why PMOS is probably not used. But this is not a very solid argument. You can design contraptions to ensure that the body gets connected to higher potential all the time. But yeah, so that is slightly different, but not a very big problem. But if you are not taking care of this, this can be a problem. Fine. Any other questions? Okay, fine. So then let's continue with whatever we were doing in the previous lecture. So wherever we stopped, we were talking about the effect of noise, right? In receivers, in mixers rather. So let's consider that, and we were discussing about the noise from the image frequency, right? I didn't make it fully clear what type of architecture that I was talking about. So there are two types of architectures in a receiver, right? One is a super heterodyne receiver and is a direct down conversion receiver, right? So let's consider the super heterodyne receiver first, right? So I'll draw this block diagram only because that helps, that will make the point anyhow. So when you have a super heterodyne receiver, so you have this to be omega LO, and this is at omega RF, where omega LO is not same as omega RF, right? So typically omega RF is essentially omega LO plus some intermediate frequency, which you can decide whatever it is. So information is around omega IF, right? Information is around omega LO plus omega IF, right? So if I draw the spectrum, so if this is omega LO, so this is omega IF plus omega LO. And similarly, you are going to have something at omega LO minus omega IF. Let's assume this is signal. This is image. Let's call this image. This signal. Okay. So when I say this is image, which means this is not something that I am expecting to receive anything from that band, right? I'm expecting to receive from the omega IF plus omega LO band. So after mixing, naturally, both of them are going to fall around DC, right? Sorry, not around DC, I made a mistake. So after mixing and low pass filtering and throwing away the higher frequency component, both of them are going to come around omega IF. Right? So if that is the case, you have a problem because obviously you cannot, you would like to throw away the image, right? So generally what is done is, that's why before the signal is fed to the mixer, you have to low pass filter out the potential image, right? So essentially you need to have a filter which cuts out the image and only gives you the signal of interest, right? So if this is the case, then the red part will not be there, only the black part will be there, right? So which essentially means that if you want to use a super heterodyne receiver after your LNA, or maybe before the LNA, right, wherever in the signal chain, because the LNA is an LTI block, it doesn't matter whether you put a filter before or after with respect to the transfer function end to end, right? So you probably want to put an image reject filter. Image reject filter. Filter here and then mix. Okay. Now it's a design choice, but can you comment on, let's say this image, this image reject filter is obviously operating around RF, right? So given that LNA LNA is an active device, would you rather have the filter, let's say the image reject filter is an ideal LC filter, right? It's an ideal bandpass filter, no distortion, nothing. So you would rather have it before the LNA or after the LNA? Linearity wise, it doesn't matter, right? You put the filter after the LNA or the before the LNA, the transfer function is the same, right? The transfer function of the filter times the transfer function of the LNA is the final transfer function at the output of the LNA. But in your opinion, whether putting the filter before the LNA helps or after the LNA helps, under what situation? Matching can be an issue potentially if you are not careful, but it can be incorporated in the matching network itself, right? There will be a matching network at the input of the LNA. It can be incorporated. Pardon? Matching network can act as a filter. What else? Pardon? Yeah, true. Noise of the filter can add before the LNA. That definitely is the case, right? So because you are going to have it is right upfront of your signal chain, right? So the purpose of the LNA was to amplify without adding too much noise. If you put something before the LNA, it's going to first add noise, then amplify, right? So that effective noise figure of the signal chain can degrade, right? Any positives of adding this before the LNA? Those are the two negatives. I agree. Perfectly valid negatives. But is there any positive at all? Yeah, right. So it gives you an additional set of filtering, right? So fine, I understand some filtering comes up from maybe a saw filter upfront and all. but it gives you some additional level of filtering. And it's a linear block, right? If you ideally in your signal chain, you would want the linear blocks to be upfront, so that it doesn't see a lot of signal swing. The nonlinear blocks do not see a lot of signal swing, right? So if you have a lot of distortion related problem in your spectra, depending upon what you are designing for, then it sometimes makes sense to put the filter upfront, right? So again, as you see that it's not a cut and dry solution that you have to put it here, you have to put it there. It totally depends on what you are designing for. Both can be done. Okay, fine. So another problem of putting the mixer upfront is this. Another problem of putting the image reject filter upfront is this. So this is as far, I mean, whatever I have told till now is assuming there is a signal at the image frequency. But not only signal, there will be noise at the image frequency, you like it or not, right? So essentially, you are going to have noise here, you're going to have noise there, right? And both these noises are going to fold back, and you are going to have some noise here, or maybe use some other color, and you're going to have some noise. Right? And these two noises are uncorrelated, right? Totally different frequencies or different bands, and they are going to add up in power, right? So which essentially means that you are going to have double the amount of noise, assuming the transfer function from the image and the signal band is same. If the transfer function is same, then you are going to have the double the amount of noise than if you did than in case of an LTI system. And this is happening because there is on the same frequency bin, right? On the same frequency bin, not only the signal is getting down converted, from somewhere else also, but the noise is getting down converted, right? So you cannot do anything about the noise in the signal bin. That will always come. But you can do something about the noise that is coming from somewhere else where signal is not there. So in that case, is there a solution to cutting out this noise from the image band? The same solution. Whatever you do for cutting out the any blocker at image, you can do the same thing for this guy, right? For noise. Yeah. So the point that I'm trying to make is, if you put the filter here, then the noise here that comes from the LNA will be here and here, both. But if you put the image reject filter here, then the noise of the LNA at the image band doesn't come in. Does that make sense? Okay, so let me maybe draw a cleaner picture. So if I sketch the noise here so this is at, let's say, B in LNA. You have noise at image and you have noise at signal, right? So output of the LNA, you are going to have the noise at the image. Sorry, I made a mistake here. I did that. So if you have this configuration, the one that I have sketched, you are going to only have noise at the signal and no noise at the LNA, because you have a image reject filter there upfront, right? So you had here you had a noise at both, but you put a filter, so this one gets knocked off. You only get noise here. This is at the input of the LNA. Make sense? Now, if I say the output of the LNA adds noise, right? So the signal noise is there, plus LNA is going to add its own noise, right? Might be less, might be more, depending upon what noise figure you have. But if it's more than 3 dB noise figure, then it is adding significant amount of noise, right? So you can have might be slightly less than whatever you had at signal, but you are going to have some noise load. Different color, right? So now when you mix at the output of the mixer, then obviously both these noises are going to come down. Sorry. This noise comes and this noise also comes. And you get enhanced noise, right? But if you use your image reject filter here, then here you have no image noise, right? Right? So this kind of gives you a better noise performance based on that. Okay. Does that make sense? Yes or no? Okay. Any other questions regarding this? So there are some terminologies. One is if when you see the literature, you are going to see two types of noise definitions for mixers. One is called single sideband noise, other is called noise figure, or this is called double sideband noise figure, right? So other is double sideband noise figure. So in double sideband noise figure, it is assumed that there is no image. This is the assumption. And single sideband, this is whatever you get, right? So typically, if the transfer function of your image and the transfer function of your signal is identical, then naturally the noise figure of single sideband noise figure is I mean, if you basically add 3 dB to DSB noise figure, you are supposed to get SSB noise figure. Right. So typically you are going to see the DSB noise figures which are reported in the literature are 3 dB lower than SSB. If the literature doesn't really specify anything, you can assume that it's a DSB noise figure. That's what the convention is. Okay. Okay, fine. Okay. So now let's talk about another way of getting rid of the image. Right. So obvious way of getting rid of the image is the one that we talked about, is put a filter here, put a filter there, and so on. Now, putting filters has a problem. One of the problems is this, right? So let's talk about a specific circuit which doesn't have a power gain. Right? So let's assume that the question that I'm trying to answer is that what happens if a circuit is lossy? Right? When I say lossy, you mean there is no power gain. Right? So I will not prove the generic case. I will show you a specific case, and then I will extrapolate it to what happens in general, right? So let's say I have a simple lossy circuit is a resistor divider. So this is RS, this is R1, right? So if I have to find out the noise figure of this network, where this is the V0, what will I do? Can help me through it? Noise factor will be, so the noise contributed by this I don't need. So let's say this is a source noise. So in the denominator, I will have the noise contributed by the source, and the numerator, I am going to have the total noise, right? Or I can simply say 1 plus the noise contributed in the denominator, noise contributed to the source. On the numerator, I'll have noise contributed by the extra element, which is R1. So you can do either. So let's do this. So what is the noise contributed by the source? 4 kTRS times R1 by R1 plus RS whole squared. And what is the noise contributed by R1, which will go in the numerator? R1 times basically RS by R1 plus RS whole square. So this guy cancels. So this becomes 1 plus RS by R1. Or I can simply write it as 1 over R1 by R1 plus RS. Right? So if I define, so now what is this telling you? This is essentially telling you is that this R1 by R1 plus RS is the transfer function. Right? So H is R1 by R1 plus RS, which I can define as, okay, let me keep it like this. So essentially this is less than 1, right? So what is this telling you? So your F is 1 over H. If H is less than 1 and H is much less than 1, then the noise factor is high. Right? If H is less than 1, noise factor is more than 1, definitely. Right? So you can basically extrapolate this and show that if you have a lossy circuit, the noise figure is approximately equal to, not approximately, is actually equal to the loss of the network. Right? So in a lossy circuit, noise figure is equal to loss. So which essentially means that if you use filters which, let's say you are going to use LC filters, the Ls are going to have loss associated with it, which means that moment you use a filter, you are going to see increase in noise figure. Fine. So it becomes sometimes tricky to justify the use of filter everywhere, even though, I mean, forget about the size constraint, even performance constraint wise, use of LC filters everywhere can cause a reduction in increase in noise figure. Okay. Losses. Still recording, right? Yeah, if you have losses, then you are going to face noise figure issues. So people thought about it and figured that, okay, so, I mean, is there any other way of getting rid of the image instead of using a filter, right? And as it turns out, there is. And trigonometrically, it is, I'll show you the way people thought about it in using trigonometry, and then we will obviously, we can extrapolate it to circuit perspective. So so I will just show a mixer. And let's assume it's an ideal sinusoidal mixer. When I say sinusoidal, I mean it's not a square wave, right? The fundamental thing that you are multiplying with is a sine omega LOT or a cosine omega LOT. So let's say this is cosine omega LOT. So your input is at omega RF and at image. There are two types of, essentially why I am calling both as an input, because both of them fall back on the same frequency after mixing, right? One is a desired input, other is an undesired input, but still it's an input which needs to be taken care. So you have the signal at cosine, let's say omega LO plus omega IFT. And there is another signal at, rather image at cosine omega LO minus omega IFT. Right? So after mixing and down converting, right? And I am throwing away the higher frequency components. So what would I get? So this guy will mix with cosine omega LOT, and I'm going to get one term which is cosine IFT. Right? I am neglecting the cosine 2 omega LO plus omega IF, because I assume there is a low pass filter or a band pass filter which is going to throw it away. I'm interested in the omega IF because that's what everything will fall back on. Okay. What will happen to this guy? What will be the corresponding term? You are going to have the same guy, right? So you are going to have another. So if I call this V sig, and this is V image, so this will be V sig, and this will be V image cosine omega IFT, right? But let's say I, instead of using a cosine omega LOT, I multiply it with a sine omega LOT, right? I can use either. It's phase shifted, right? So let's say I use sine omega LOT, and input is still whatever I have. So at the output, what will I get? So if I concentrate on the signal first, what am I going to get? Sine A plus B, sine A minus B, right? Sine A plus B is at a higher frequency. Sine A minus B will be at a lower frequency. And what will it be? It will be sine omega IFT. Right? What about the image guy? Oh, sorry, I made a mistake here. I multiplied the image here. Right? So this guy will be negative, but this gets multiplied with this. What about the image guy? The image guy will have a V image times sine omega IFT, plus or minus. So this gets multiplied with this. Sine A plus B is a higher one, and sine A minus B is a lower one, right? So essentially you get plus sine omega IFT. So again, in circuit design or in signal processing, when you see the desired one has a different polarity than the undesired one, then your mind should light up that something can be done. Then I can split in some way. So clearly in this case, you cannot split by simply adding, because the top guys are cosine, the bottom guys are sine. But can we convert sine to cosine? How? Simply 90-degree phase shift, right? 90-degree phase shift at what frequency? At IF, not at RF. And that is a significant difference, because when I say 90-degree phase shift is essentially quarter cycle delay, right? For any frequency, when I say I am doing a 90-degree phase shift, in delay, I am essentially saying that I am moving the sinusoid by quarter cycle, right? Full cycle is 360, half cycle is 180, quarter cycle is 90. So designing a delay at high frequency, just like anything else, is difficult job. But designing a delay at low frequency is a much easier job. Okay, I am not showing it, I'm just making a statement based on your experience of designing circuits, also I presume you would agree that designing something at lower frequencies is probably comparatively easier than getting something done at higher frequencies. So at least we are in some signal processing needs to be done at the lower frequency, right? So can be done. So let's say what I do, I'll take this and do a 90-degree phase shift at IF. So the output will be, now depending upon whether you are adding 90 or subtracting 90, this output can be V sig cosine omega IFT. This can be minus VIM cosine right? So now when you have this, so far so good? Okay, so now when you have this, now it should be obvious that this signal and this guy has the same polarity for your signal, but opposite for image. All you have to do is simply add them up, right? So all you need to do is take this, add them up, and you get 2V6 cosine omega IFT. No image. Question? Yes, no, okay. So again, no filters, right? No filters, but you are able to get rid of image. This architecture is called Hartley architecture, and I'm pretty sure all of you have seen this when you are doing basic communication courses, amplitude modulation, phase modulation, and all those things at some point of time. Principle is the same, but there are various variations of this. Circuit design wise, you can design the same thing in different ways. There are multiple variations of this you can do. Right? For example, you can, instead of delaying omega LO, I can delay, instead of having two phases of clocks, I can have a delay here. Have the same phase of clock, but a delay at the input. Trigonometric wise, there is no difference, right? I am basically introducing a split between the phases, right? So that is one option. Then there is another option of how do you add, right? Mathematically adding is just put a symbol, right? In circuit design wise, how do you add? You can add in current domain. That is the easiest thing to do. Alternatively, if you can, if digital, this is at low frequency anyhow, right? Omega IF is at lower frequency. If it's, let's say it's few megahertz. So in that case, you can directly put an ADC, right? You directly put an ADC and you get everything in digital bits. When you have in digital bits, then everything is math after that. Then you do your signal processing in digital. That is another option. But it all depends upon what is the requirement. When I say requirement, what I mean is that as the further down the signal chain you carry your image, which means you are carrying an extra unwanted stuff into your signal chain to be cancelled somewhere else, right? So you're carrying the burden and assuming that I'm going to cancel it later on. If you can, you cancel it upfront only. Then you don't carry the burden along with you, right? So why I say burden is because this image will all, if you do not cancel it, forget about the noise. If there is a signal at the image, that signal is going to cause distortion to all the active components through which it flows through, right? So it is better to, that's why if you can cancel it upfront and not wait for digitization later on, right? But that's again a topology choice. Okay. Sometimes you can do bit of both in the sense that you can have a filter, image reject filter, and we know that none of these filters are perfect, right? It's not as if this is going to cancel out the entire image. There will always be some residue. You have the filter and then do this image cancellation in digital. That is also possible, right? So in any RF chain, none of these cancellation is done at once. It's done at various parts of the chain, and you keep cancelling. Okay. It's like almost cooking, right? Basically, you have the same ingredient. When you put it, makes all the difference. Okay, fine. So now, what are the potential issues with this architecture? Looks all good, but you must be, and I mean, at this moment, you should always, whenever you face a new architecture, you should always question what are the potential issues. Obviously, this architecture is based on canceling something that is happening between two paths, right? You have something in the top path, you have something in the bottom path, and you are assuming that the unwanted parts are exactly identical when I am about to cancel. What can go wrong? There can be phase difference. This 90-degree need not necessarily be 90 degree. It can be 89 degree, 89.5 degree, 90.1 degree, right? So which means that your cosine will not be exactly cosine. It will be cosine plus some small phi. Yes. Good question, right? So I'll answer that before today in next 5 minutes. But let's assume you can. So if you can get a even if you can get a phase difference of 90 degree, it will never be exactly 90 degree, right? Like everything else in circuits, it will never going to get exact. So if that is not the case, obviously intuitively you can see that there will be not a perfect image cancellation. There will be some residue. Similarly, these two amplitudes of sine and cosine also need not be exactly identical. There can be a mismatch in the amplitudes also. If there again there is a mismatch in amplitude, when you subtract, you are not going to cancel out the image perfectly. For example, if you have a 1% difference between the amplitude, there will be a 1% amount of image that will be there, which means you can get maybe 40 dB of rejection, image rejection. 1% is approximately 40 dB, right? So if you have 1% difference in amplitude, the maximum image rejection you can get is 40 dB. Similarly, I do not have time today, but similarly, you can also show that if you have differences in phase, you can have such impacts, right? Now, coming back to Dhruv's question, how are you going to create a phase difference? So again, what is a phase difference? If I say the two waveforms, they're 90 degree apart, in time domain, what do you interpret it as? It's a delay, right? So here I have shown with respect to only sinusoidal clocks. But in principle, you are going to have square wave clocks. So let's say I have a square wave clock like this, and I delay it by 90 degree. What should it look like? Complement is 180 degree. So 90 degree phase shifted clock should look like this. Right? So the fundamental of this guy will be whatever, fundamental of this guy will be 90 degree of phase shifted also. Right? So why I say that? So basically this is summation of Cn e power j n omega LOT. So this will be Cn e power j n omega LO t minus pi by 4. Sorry, t minus
By 4.
t naught by 4, yeah. TLO by 4 basically. Right. So you take TLO by 4 out, and then you see you get for the fundamental, you get 90 degree phase shift anyhow. Right. So in digital, do you see is this easy to make in digital, or you can tune the clock too, but is there a simpler way of getting this 90 degree phase shift? When you have D flip-flops and all, you can, right? Right. So essentially, all you need to do is start off with double the frequency, because you need to, when you D flip-flop works only at the edges, right? So the time duration, the definition of time in sequential circuit is the edge of the clock. You cannot resolve anything which is slower than the edge of the clock. I mean, difference of the clock period, right? Does that make sense? You're making every decision at the edge of the clock cycles, right? Always at first edge of clock, always at next edge of clock, and so on. So if something happens between the edges of the clock, that doesn't exist, right? So 1 second is essentially one clock edge, kind of, right? So here, obviously, we are trying to see that something we are trying to get at middle of the clock. So that's not going to be, you are not going to get this simply. But if you start off with double the frequency, let's say your original clock is double the frequency. And so on. Then you see there is some event happening at the edge of the clock. Right? So then you use a D flip-flop or something to delay the initial clock, and then you divide by 2. Divide by 2 is basically using a counter, right? Divide by 2 counter. So you get a delayed version. Pardon? Yeah, it's basically a XOR operation, I agree. But XOR operation, it is done. I'm not saying it is not done, but instead of doing a combinational, so when you do a XOR operation, essentially, you are doing a combinational operation, right? You can do a XOR, it will work. But sometimes what happens is, then you are beholden to the delays of the XOR network also. Right? So if you are doing at very high frequency and all, so you'll have to take care of something additional instead of using only a XOR. Maybe XOR is going to give an additional delay. It doesn't come for free, right? It is going to give an additional delay. Then you have to tweak for that additional delay. Instead, if you use D flip-flops only and identical number of D flip-flops on the top path, identical number of D flip-flops on the bottom path, then you don't have that problem. But having said that, XOR is used, right? The reason I said this is because it is easy to relate. Okay. Okay, fine. Any other questions before we stop? Okay. Thank you.